Okay, here's your review for exam number 4. Notice the format is the same as it's always been. There will be a strict time limit. You can bring a note card with you. You can't bring a calculator. There will be no complicated arithmetic, certainly. And as always, you show all your work. Okay, so no change there. As far as the material, we had an exam not all that long ago. There's not all that much. And just kind of working in reverse, the very last thing we talked about, the last 10 minutes of class, was this idea of the integral meaning something besides area for us. And we talked about position. If we knew the velocity function, then the integral we knew would tell us something about distance, depending on the nature of the velocity function. And then we generalized even a little bit more to talk about the value of an integral. If we know the derivative, the rate of change, then the definite integral will tell us about the accumulated change. And I assigned a few problems. They weren't the greatest problems, maybe, and not that many. I think there's some more in the book that haven't been implemented in the homework, and maybe you can find those in Chapter 5 and do some of the problems in the textbook. Maybe I'll look one up here if I can and do it for you shortly. But the material we have covered is, after net change, certainly the fundamental theorem of calculus, which of course says that we evaluate a definite integral through the use of antiderivatives. Okay, examples coming. Of course, we use the whole idea of area to motivate the idea of integration, to lead us to a definite integral. And then all of this stuff down here, that's what it's all about. Definite integral. What a definite integral is this limit. I mean, it's a complicated thing. And fortunately, the fundamental theorem tells us a way that we can do all of this calculation here without having to do it, if we can only find an antiderivative. So let me pause this for just a second and get a clean slate. All right, to finish the material from the last information is the whole idea of antiderivatives, and you can see I've given it 4 exclamation points. So hopefully that you can recognize that that's going to be a big part. And even though we had some antiderivatives on the last exam, because we've done so much more with them, that section, the very last section of Chapter 4, if I remember correctly, will be just as big a part of this exam as the things that we've covered in Chapter 5 in the meantime. And I had an example here I thought I'd work through. There are a couple on the homework like this. And this one actually is a little bit tricky, perhaps. And I wanted to show you how we go about doing it. And, we don't know a function whose derivative is ln x over x, so we need a substitute. And not 100% clear, doesn't really feel like there's a composition. But if you think about the derivatives of these with the idea that we're going to do substitution, and so the derivative that comes from the differential is going to be a part of this, then hopefully you could think that ln x will make a really good substitution. As soon as we substitute, we calculate the differential. Of course, the derivative is 1 over x dx. And then notice what happens. Switch to red. So this ln x just is u. And then let me do a couple of steps here, maybe not 100% necessary for all of you. Once I plug in the u for my ln x, then what's left over is 1 over x dx. That is this. And lo and behold, 1 over x dx translates super nicely to u. It's just du. And so therefore we get 1/2 u squared. And now that we've got our antiderivative, we can plug in what u is, which is ln x squared, and then we'll tack on our plus c. So I don't really get the substitution here by thinking about compositions like we do in almost every other problem we did. Rather, I get it by thinking about derivatives. And I notice how this piece right here, I can write it as the derivative of ln x, and it just makes this super simple integral in the end. Okay, that's one example. Maybe I'll do one or two more here. All right, we had a problem like this on the homework, and had one student ask me about it, and maybe everyone figured it out and I'm wasting my time talking about it, but I'm going to talk about it just the same. I want to show how the things we've learned before can really just make this problem really easy for us, I hope. So the graph shown is of the function f of x, identified here. And then we define this area function just like we did in our development up to the fundamental theorem. So for each x, it tells me the area. Now, because some of the areas below the x-axis, then, we read those areas as negative, but you get the idea. And the question then asks about the find all local extrema and classify. That's not exactly how the book asked it, and I'll explain it here. Of course, we know what local extrema are. Classify, it means identify, like every local extreme value is a min or a max. And so we want to know which is it. Okay? And I left off something super important. I want to know about the function a, not about the function f. Function f is obvious. We have a min right here, a local min, a local max. But that's not the interesting function. The interesting one is the area function. So, to find extreme values, we need the derivative. And by the fundamental theorem of calculus, the derivative of a function defined in this fashion as an area function is just the function generating the area for us, little f of x. And to find extreme values, those are critical points. So we're going to set x equal as set the derivative, which is f, the derivative of the function we want extrema for. We know it's f of x, and then we're going to set it equal to 0 to find the extreme value. There are three critical points. 2, 5, and 8. So let me go to red here. That is, a is equal to 0 here. Sorry, the derivative of a prime, the derivative of a primed is the function shown, and wherever it equals 0, we have a critical point. So we have one at 2, we have one at 5, and we have one at 8. We know that all extreme values occur at critical points, but not every critical point corresponds to one. In fact, we have tests to determine the behavior at critical points, the first derivative test or the second derivative test. Because we don't have any algebraic form for the function, I don't think we're going to want to think about the second derivative test, but the first derivative is super easy to apply here. It just says, does the derivative change signs at a critical point? If it does, there is an extreme value. If it changes from negative to positive, it's a minimum. From positive to negative, it's a maximum. So look, x equals 2 is a critical point right here. And the derivative of a, which is f, well, it's negative below, and then it turns positive. So at x equals 2, we have a minimum by the first derivative test. And then we move over here to 5. And we see here to the left, the derivative is positive. The function is increasing, turns negative, so we have a maximum, a local max. And we have one more critical point. At 8, the derivative, it comes up and kisses 0 and turns around. But now the derivative does not change signs. So it's negative to the left and negative to the right. So even though it's a critical point, there is no local extreme value. So none at x equals 8. So it's getting sort of crowded here. Let me create a little space. So the graph at x equals 8, it's the derivative leading into 8 is negative, so it's decreasing. And then for just an instant, the derivative is 0 at 8. But then it continues decreasing, so we get that sort of behavior. In fact, notice that at this critical point, which does not correspond to an extreme value, it's actually a point of inflection. We'll concave up here and down there. But this question's not asking anything about that. But there is an instant where the tangent line is horizontal, but no extreme value because the first derivative doesn't change signs. All right, I'm going to pause here and get a clean board and do at least one more problem, one of the net change problems. I'll look one up from the book. The last thing I might say, and I don't have a particular question in mind, but remember we're talking about definite integrals on this test, and a definite integral is the limit of a Riemann sum. So I would encourage you to come to the test prepared to show that you know what a Riemann sum is and that you can construct one for a given function over a given interval. You actually did that on the last exam, so it should be something you're ready to do. And again, like I said, I don't have a question in mind, but it just seemed like a good thing for students to know, because definite integrals are a big part of this exam, and of course a definite integral is the limit of a Riemann sum. All right, I'll post this and make it available for Monday morning. Later in the day, I plan to just work some problems and post the solutions. So I'll try to get those posted on Monday so you have time to look them over and maybe learn from them, maybe not. Maybe you'll just get confidence that you're ready to go. And also, I'll be sending out an email sometime on Monday about exam options and details, so be sure and watch for that. All right, happy studying. Talk to you later.